This is just a little finish-up video from today's lecture so that we can complete Chapter 23, and you'll be ready to start Chapter 24 for Thursday. So basically where we were when we ended class is we had just gotten to the idea of equipotential surfaces. We had also, a little bit before that, defined what we mean by electric potential. So remember that when we talk about electric potential energy, it's the interaction of charges with electric fields or the interaction of two charges. When we're talking about electric potential, that's exclusively like talking about the electric field and how it's changing in space. So we got to this idea of equipotentials being locations where on these surfaces, everywhere, the potential has the same value. Just as a reminder, we had said that the change in potential is equal to minus the integral of E dot ds. And so one of the things that this told us is that the electric field points in the direction of decreasing potential. And then when we got to the idea of equipotentials, we said, what if E is perpendicular to our displacement, that would mean then our delta V was equal to 0, and so we would be moving along what we would call an equipotential. So by definition, equipotentials are perpendicular to the electric field lines. And so that's what you see is true here. So we could think of two things that would, putting these two facts, this fact and this fact, together, we could say, for instance, this potential here, this dotted line, might represent a potential of 3 volts, while this one might represent a potential of 4 volts. This would show you that as we move outward in the direction of the electric field, the potential is decreasing. And also these surfaces you can see are perpendicular to the electric field lines. Another idea, another thing that is actually true about equipotential lines is that it doesn't take any work to move a charge along an equipotential line. So going again from this idea, delta V is equal to minus E dot ds, just remember that where this came from was the definition of potential energy, which was minus QE dot ds, which was also equal to minus the work. So the idea is that, the work could be expressed as minus Q delta V. If we move the charge along an equipotential where delta V is equal to 0, then the work is 0. So the idea is that, like, if I took a little charge right here, if I move it, anywhere I move it along this line doesn't take me any work to do that, because moving along this line, the delta V is equal to 0, and then therefore also the work that would be necessary to move it would be 0 as well. Okay, so again, this is just a picture sort of reinforcing the idea that our potential is decreasing as we move along the electric field, or if we moved against it, our potential increases. So here, another way we can talk about the change in potential energy. For some reason, this doesn't really do our subscripts very good, so let's just rewrite that. So if we're going from point B to point A, we could say that we are moving the charge from VA to VB. Well, it goes, this is final minus initial. This would be equal to my change in potential energy, which would be UA minus UB. So if we move a charge from a different potential to another potential, then there's going to be a change in potential energy. So this kind of goes from our original definition of potential as the potential energy per unit charge. Here, we're just sort of rearranging this and look at changes. And so Q delta V is equal to delta U. This is something that's going to come in handy later on. For instance, we might think about a situation where I have some sort of, parallel plates so that they have an equal and opposite charge, and we know that there's going to be some sort of electric field associated with that. And so as we go from one point to another, there's going to be some change in potential. So the idea being, if I move a charge between 2 points in an electric field, that charge will experience a change in potential, which is just going to be determined by the different locations that we were located in the electric field when we started and when we ended, but also that charge is going to undergo some sort of change in potential energy, and this is the relationship that can help us. Keep in mind that we would also then be able to use a relationship that we haven't looked at for a while, but when we learned about energy, the fact that that change in potential energy is the negative of the change in kinetic energy. So if the potential energy decreases, that's going to talk about an increase in kinetic energy and vice versa. So we're thinking about that. And that's something that we will look at. There'll be some problems dealing with that. Of course, this is going to be measured in joules. This is in coulombs, and then this is typically measured in volts. Sometimes, though, we take a shortcut. You might see sometimes an energy expressed in electron volts. And that's just sort of an easy way to talk about the situation, because 1 electron volt is the energy that you would get if you take something with a charge equal to that of the electron, so it could be an electron or a proton, and you send it through a potential difference of 1 volt. Its energy the change in energy that it has would be 1 electron volt, so it's kind of easy. For conversion factor, we use the fact that 1 electron volt is 1.6 times 10 to the minus 19 joules, which that should look sort of familiar, because 1.6 times 10 to the minus 19 coulombs is the charge on an electron. Okay, so one of the things that we want to think about is, now that we understand something about potential, can we say something about now that we know the potential, can we sort of go back and look at things like our charged conductor and make any sort of conclusions about what the potential in my conductor looks like? So just reminding you, we talked about conductors at the end of last chapter, and we said that when our conductor is in electrostatic equilibrium, the electric field inside of the conductor is 0. Right here we see that. And all the charge remains on the surface when it's in equilibrium. And so actually you see here that once we get to the surface, the electric field looks just like the electric field of a point charge. So what can we figure out about the potential inside of the sphere? Well, we could say we know delta V is minus E dot ds And so if we go inside the sphere, because E is 0, this means that delta V is going to have to be 0. But we have to have some sort of continuity. And that, remember, that doesn't mean if I'm going from point A to point B, that's going to be VB minus VA equals 0. So it doesn't mean necessarily that the potential is 0 because the change is 0. It means that the potential is actually constant. And so, and then it would have to also be continuous, so that we would say when we got to the surface, it would have to be equal to the potential at the surface. So just because the electric field is 0 inside of the conductor doesn't mean the potential is 0. It actually requires then that the potential remain constant inside of the conductor. So here's an example to see if we could figure out which graph is going to be best. So this is a similar question where we have a metallic sphere and it has a radius of 5 centimeters. And the potential at the surface is 100 volts. And it wants you to say, like, what does the potential look like from the very center of the sphere till, like, way far away. So what we learned in the last slide is that the V inside should also be equal to 100. So that brings us to sort of eliminate this graph and this graph, and now we have to figure out which one of these is correct. And so the potential then is going to outside look like that of a point charge. So we can use that because it's going to fall off as 1 over r. So when we're at 5 centimeters, it has a value of 100. And then it's like, okay, so what's going to happen when we get twice as far? So if r goes to 2r, what is v going to go to? So that's going to be v over 2. So we should go from 100 to 50 when we get to 10 centimeters. And so that is going to be our correct graph. And here we see that picture there. All right, so our last thing is using this relationship delta V equals minus the integral of E dot ds. And what if we know V, can we find E? So sort of taking this and writing it more in a differential form without the integral, this could look like this. So with a very small increment of distance, we would have a very small increment of potential change. Let's assume that E is EX, and then ds is going to be in the dx. So we're just going to assume one dimension to make things really simple. So this changes to dv equals minus ex dx. And if we rearrange things, we can say that the electric field is going to be just minus the derivative of the potential with respect to x. If we have other components, this can be generalized to Ex would be minus dv dx, Ey is minus dv dy, and ez would be equal to minus dv dz. These are partial derivatives, which we've looked at a couple times. This should look like something sort of like we did before, where you might remember that in a previous chapter we found that the force could be written as minus du dx if it was in the x direction. So we did something similar in a previous chapter. So that's enough. That's just the missing things that I wanted to make sure you knew before you move on. So I hope you watch this, and I will see you next week.